Greetings, in this one I'll be doing a quick definition of a so-called ideal of a ring. So it's a subset with some properties regarding rings. So first of all, there's the definition of ring, which I definitely would recommend you to go over first, because that's a prerequisite. And now we'll be talking about the ideal of a ring. So it's called ideal of a ring. We will be denoting ring as R. So ideal will be denoted as I, that's the common way, and it's a subset of the ring. So by this I mean the ideal of the ring as a subset of a ring which is denoted R with these two properties. So first of all, ideal under addition is a subgroup of the ring under addition. So if we look at the ring, the underlying set of the ring as a group with addition, then a subgroup of it is the ideal subset. And second of all, we then have this other property, that is, we should take into account that not every ring is commutative, and the operation between elements of a ring are not always commutative. So we should talk about left ideal and right ideal. Only if the whole ring is commutative and things are acting commutative, then we can talk about left or right ideal as the same thing. But if we're talking about left ideal, so let's say this is because I'm talking about the left ideal. Well, usually in abstract structures, when we define things like cosets or this, and it's not commutative by necessity, we will talk about left and right. So left coset, left ideal, right ideal, and usually the left version is the first one looks at. So just like one first looks at left cosets, now we're talking about left ideal. So left ideal is basically that if we take any element R from the whole ring, which can be outside of this subset, and any element A in this ideal subset, ideal, the name, it's not as an adjective, but the name, ideal, this subset I of R, we must have this, that RA will go into the ideal subset itself. It will not go into any element of the whole ring R, but it will be closed inside the ideal. So when an element under multiplication acts with another element from the ideal, with another element of the ring, the result will be inside the ideal subset again. So I'll give an example in a second, but notice we talked about left ideal. That means that some element from the whole ring acts on that element from that ideal from the left, on the left side. So we see this R from the ring as a whole is on the left, acting in multiplication with an element from the ideal, which is on the right in the multiplication. So the R in R is on the left, RA. If it was a right ideal, this could be A times R. And if it doesn't matter, if it was commutative, everything, then it wouldn't matter. RA would equal AR, but that's not necessarily the case. So let's talk about an example. So an example would be, let's first of all take a ring. So an example ring would be integers with addition. So we will have the identity 0, and with multiplication. So this is our ring, and I can just say that, like integers, and I just mentioned verbally what are those underlying operations there that are necessary. So we have the ring of integers, and then what could be our ideal as an example? Well, it could be I is a subset of R. We have that also here. So instead of writing again, I could actually already write what is the ideal itself. It could be, for example, the multiple of all integers. So all odd integers. Because that works, that fulfills the rules. What we need is a closed operation with multiplication. And when you multiply an even number, even integer by any other integer, it will end up even always. So that fulfills this rule. And of course, we also have it as a subgroup under addition, because we do have inside this is like all the numbers minus let's say 3 dots minus 2, 0, 2, 4, 6. So 3 dots like this. And of course it contains 0, which would be the additive identity. So that would be fulfilled. So yes, according to these rules of the ideal, this is a valid example. So if we take, for example, as an example, even multiples of integers, that's a valid ideal of a ring.